Vestigial sideband, why it is called as the vestigial sideband and how it is different from the SSPSC, as well as we'll see how we are going to generate the VSB signal and how we are going to detect with the help of their time domain and frequency domain representations. Okay. So still you didn't subscribe our channel, please subscribe it and share it with your friends. So VSB name is what? Vestigial sideband. So here completely one sideband is not blocked here, but some portion of that sideband is blocked. So it's going to compromise that DSBSC means it has two sidebands and SSBSC means it has only one sideband. So but here in VSBSC one sideband and partial of another sideband is also available, and its bandwidth is slightly higher, 25% than SSBSC signal. And you have seen that SSBSC used for the transmission in case of high frequency component like we have voice signal. But in case of low frequency components, this USB and LSB both are going to overlap. Okay, they are going to meet at the carrier frequency. Then it will become difficult to isolate USB and LSB signals separately. So this problem we are going to solve by the help of VSB. So here one sideband is allowed in place of rejecting one sideband. And here if you see the waveform, this is the baseband signals and this is the spectrum of the VSB. So if you have suppose only one sideband, so this is the going to look like this in case of lower sideband. But whereas in case of VSB, what we have, this sideband portion along with another sideband also portion is there. Okay, that's what is called as the vestigial sideband. And here bandwidth is between Fc minus W and Fc plus Fv here. So finally, if we'll subtract from here, we'll get the W plus Fv. That is the final bandwidth here for the positive frequency. Similarly, here we can see for the negative side also. Now here we are seeing how to generate the VSB signals, and we'll see with the help of their frequency domain representation. So VSB we are going to obtain by the help of DSBSC signal when it is going to pass through the particular filter. So that transfer function is h of f. So it is important here to design the filter with h of f. Okay, so they're having some specification that we are going to see. So a spectrum of VSB signal, so that is in frequency domain, we have AC by 2. Inside we have M of F minus Fc plus M of F plus Fc multiplied by this filter function H of F. So M of F is the Fourier transfer of M of T that we know, and H of F we are going to determine, so that is it should be suitable to detect the message signal by using the coherent detectors without distortion. So later we'll see the waveform also of the H of F transfer function, how it is going to work. So here for the generation, we have balance modulators and input signal, message signal is given here. This is the carrier signals, and here output of the balance modulator will be DSBSC that is going to pass through this low pass filters of the specific transfer function. That transfer function H of F. Then output of this filter is the VSBSC signals, modulated signals, okay? And later we'll have about demodulation parts. So in demodulation, again, this modulated wave is given to balance modulators, and this is the synchronous detector like. So same carrier signal is given here in input. So now finally this demodulated signal, like how we have in case of DSBSC, is going to pass through the low pass filter, okay? So this low pass filter is the simple filter which will allow only low frequency to pass, but this H of F is very important when you are going to design about this. So that product modulator output is AC dash S of T cos 2 pi Ct, and if you take Fourier transform of the equation 2, then we'll get the frequency domain, that is AC dash by 2 into S of F minus Fc plus S of F plus Fc. Now we are going to substitute this equation 1 into the equation 3. So there what we have function, that M of F minus Fc m of f plus fc. In that, we are going to substitute. So finally here, SC of f is AC dash by 4, and this is the in place of f, what we have here, f minus fc. Again here in place of f, we have f minus fc, and remaining this minus fc is already in equation 1, plus fc is also in the equation 1. And similarly, h of f become h of f minus fc. So again, further, we have two terms are here. So for the one is for the first term is about this one, s of f minus fc, and last two terms is for the s of f plus fc. For this, we are able to obtain this part. Now we are just trying to simplify here. Okay. After that, this is the equation, and finally, at last, m of f is taken common. For that, we have function in this format, and remaining two terms are given by using the equation 4. So if you see that in the first part here of this here, what we have here, m of f. So m of f is what here? Fourier transform of the baseband signals. So first term is important for us, okay? And second term is the spectrum of VSB signal with carrier frequency. That carrier frequency is what here? 2fc. Okay. So directly here we have m of f, but here we have, with the help of that part, is going to represent the VSB signals, and carrier frequency is what here? 2fc. If you compare with equation 1. Now this second term can be removed by using the low pass filters. Okay. So this low pass filter is being applied. So finally we'll obtain the first term alone. So this again, the similar kind of the waveform what we have seen earlier. So this is for the upper sideband. Earlier we have seen the lower sideband. This is for the upper sideband here. Okay. And this side again function is there. So for the distortionless reception, it is important that this transfer function of the filter should satisfy this one. H of f minus fc plus h of f plus fc should be equal to 2h of fc. So that is important here to obtain the distortionless reception. So if a spectrum of m of is outside this range of minus w to plus w, then equation 6 should satisfy this above range. And here we are going to normalize the value of h of f. And if you see that filter response here, so for the particular range, fc plus fb to fc plus w, its value is what here? Unity. And below this value is going to increase, and above this value is going to decrease again exponentially. So this is how we have to design the h of f filters. Now we have time domain description of the VSB signals. So here, like how we have discussion about this SSVSC signal. So we have in-phase components and the quadrature components. So similar discussion is here. S of t is the modulated wave, Si of t cos 2 pi fc t minus Sq of t sin 2 pi fc t. So in-phase and quadrature, and frequency transform, like we have seen earlier also, that is the equation 2. Okay. So now this in phase and quadrature components, how we are going to write, that is the important. So this baseband signal having only range in minus w to plus w. So here in phase component is given as s of f minus fc plus s of f plus fc, and remaining place, what is it? 0. Similarly, quadrature components again in the same range minus w to plus w. So this is the quadrature. So that is along the y-axis imaginary parts. So we have s of f minus fc and minus s of f plus fc. If you're able to remember in case of SSVSC, so that response, how we are able to obtain. Okay, like this response is there. On the basis of that, you're able to see. So now we are going to utilize this equation 2 and 3. Okay. So this, what are the components that we are going to substitute there? So by using equation 2 and 3. So finally we have, this is the in-phase components. So here you are seeing that we are substituting the values. Okay. Next we have again here we are going to assume if h of fc is 0.5, then equation 5 we can write in this form. Okay, so this is the what will happen here. It is going to be only f 0.5 values. So now finally you will have AC m of f. This inside one will be going to be cancelled. Okay. So now since we have seen the by the help of graph also you can determine. Okay. So here SI of in phase component is half of AC into m of f. If we take the Fourier transform of this one, we'll get the time domain, that is half AC into m of t. Similarly, we are going to use for the quadrature component, we are going to use the equation 2 and 4. So we have j by 2 AC m of f, and here this is for the filter response. So this can be generated by passing the message signal through the filter, whose transfer function is given as HQ of f. This is the equation number 9. So this is the transfer function of the filter. Through this, if the signal is going to pass, we can obtain the quadrature components. So here we have frequency response of that filters. Okay, between minus FB to plus FB. You are saying here it is positive for the negative frequency, and it is the positive negative for the positive frequencies. Both are opposite of each other. So now here MQ of T is the output of the filter. The transfer function is what here? SQ of F due to the M of T. Then we have quadrature component AC by 2 MQ of T. So finally, by using these two equations 7 and 10, we got the value of the in phase and quadrature. So that value is substituted here. So here sign is minus. So this is the USB components. So this can be seen here in terms of block diagram. How we are going to detect this part means how we are going to generate this VSB signal here. So that is the modulating signal. Message signal is given here. So two balance modulators are used. If you see in the SSBSC, in place of filter of HQ of F, what we have used there? Wide range low pass filters. So that is going to generate the Hilbert transform pair. But here directly filter is utilized with transfer function HQ of F. That is important. And that is MQ of T is given to the bias modulator 2. Okay. And this is bias modulator 1. Then we have oscillator that generate the carrier frequency AC cos 2 pi FCT. That is given to bias modulator 1. And bias modulator 2 is given the carrier frequency with 90-degree phase shift. That is AC sin 2 pi FCT. And finally, output of both bias modulator is given to the summer here. So if you have minus, we are going to get the USB. If you have plus, we are going to get the LSP. Okay, so already we have seen the both type of the VSB waveform if you are going to consider upper sideband or lower sideband. Next, we have about the detection of this VSB signals. So how we are going to detect that time domain representation we are going to see here. So this is based upon the synchronous detection techniques. And finally, later we are going to utilize the envelope detectors. So that envelope already we have seen earlier lecture also. So that is available in the playlist. Okay. So it is used mostly in case of TV broadcasting. So in case of TV broadcasting, what we have, audio and video, both signals are available. So now carrier signal is assumed here, AC cos 2 pi FCT. So finally, this VSB signal is going to appear with this carrier signal. So AC cos 2 pi FCT plus half AC K M of T cos 2 pi FCT minus half AC K M Q of T sin 2 pi FCT. And here Ka is what here? A scaling factors. So here finally we are taking some common terms. So from the first two terms, common term is taken. So we have here cos 2 pi FCT and quadrature component is here separate. Now this term, as this is equation 1, can be written as E of T cos 2 pi FCT plus theta, like how we have written in case of carrier reinsertion method for the SSBSC, where we are trying to detect. A similar condition is here. So E of T is what? A square root of sum of the square of both components. This is the one component and this is the another components. Both a squaring, adding together, and then a square root. This is just like if you have, this is the x plus jy. So how you are getting this? X square plus y square. Similar condition is here. This is for the in phase. This is for the quadrature. And angle is what? Tan inverse y by x. So same condition is here also. And finally, this envelope can be written in this format. Okay. So again, we see that this is also very important. Separate question we'll have about the comparison of various AM systems. So comparison of various systems, if you see that how we have simple linear modulation wave, then what is happening there in case of DSVSC, what benefit we are going to get here. So if you see that demodulation of AM signal is simpler, but here AM-SC is not simple. Since here we have different hardware we are going to use, so it is expensive, and AM signal is able to generate with high power. Okay, since there was the power requirement was there. So here in case of linear modulation SC, what we have like DSVSC or SSVSC, what is happening here? Less power is being transmitted since carrier is suppressed here. So here we have 67% of the power is consumed by the carrier. So that carrier is suppressed here in suppressed carrier type. Okay. So it is less efficient. Which one? Okay. So now here AMSC system receivers are efficient but complex and extensive. So all suppressed carrier when you are trying to design, so that devices are little complex, so it is going to be costly, and it is used only for the point-to-point communications. So we are able to save the power, and later in case of SSBSC, what we are saying that we are able to save the bandwidth. So here AMSC, DSVSC requires bandwidth of 2W. In SSBSC, bandwidth is required W only. VSB having between both, okay. We have seen that it is little higher than W, less than 2W, okay. So that is we have seen W plus FB, which is the bandwidth of the VSB. So SSBSC used for the long distance transmission, especially for the high frequency, and conventional AMs fails to meet the definition of the linear modulation. So it is restricted there. So since M1 of T, this is M2 of T, is not equal to S1 of F plus S2 of T. So that is a small deviation. And here different techniques are considered, like for the method of generations in the AM, what we are using, square law, modulator switching, DSBSC, balance modulator, ring modulator, SSBSC, frequency discrimination and phase discrimination method. Okay, so these are the different comparisons are done here. Again, the method of the demodulation, how we are going to generate. So all these comparisons are done here. Again, bandwidth, if you see that for the both sections, all comparison are done here. So here only a small thing we'll see about this VSBSC TV video transmission here, how it is going to occur. So here y-axis we have relative amplitudes, in the x-axis we have frequency. So if you see that here different range are there, we have relative channel. So this part we have video LSB, here we have video USB, and this frequency is 0.5, here 1.25, here 5.25, 5.75. It is not much important for the examination point of view, this diagram, but is if you try to understand about the television set, so there you can see that how it is going to occur. So here video section is separate, here audio section is separate. Okay, so here we have sound carrier. So that spectrum is about width is 50 kilohertz. Okay, and this part is about the video, that is the picture carriers. So that range you can see how it is going to work. Okay, so that is the meaning here, how VSB is useful in case of television video transmission. So this is all discussion about VSB. Okay, later we'll see about the numerical part in the separate lectures, and all lectures of previous one is available in the playlist. Please go through that. Any doubt is there, you write in the comment box. Okay, like, share, subscribe. Thank you. Thank you very much.